Billinghurst algebra students. So these are going to be your notes for the exponential growth and decay. You are looking for these two foldables in your ISN. One says exponential growth and the other one's going to be decay. You should have already watched an introduction to this idea of exponential growth, and now I'm going to give you some of the notes to start you off on growth and decay. So when we're talking about exponential growth, some things that you may have heard of before is population can grow exponentially, so that's growth. Or if you've ever heard of half-life, something that's radioactive, that is a decay, and it goes exponentially. When we're looking at table of values of exponential growth, you can see the numbers when x, the independent variable, is 0. Remember that anything to the power of 0 is going to always be 1. So these graphs are going to go through at 0, 1. Then when x is 1, you have 9. When x is 2, look what happened, 81. When x is 3, well, 9 to the power of 3 is 729. And you can see how this chart is growing exponentially. Look at the number when you get to x to the 8. In the opposite idea is decay. As the x gets bigger, the numbers get smaller and smaller and smaller. So that's going to be, you should have now your ISN notes, and we're going to look at exponential growth and decay, the table of values, and the graphs. Let's just a reminder about some of these graphs. Exponential are going to be nonlinear. We should now recognize linear functions. There are a lot we know about linear functions. Y equals mx plus b. So when we're looking at the table of values or the equations, you should be able to recognize a line. This is a quadratic. This is going to have y equals x to the power of 2 in it. It is a square, and graphs a parabola. This is a nonlinear function. So then when you see a graph that looks like this last one, this example is a function of an exponential. What I mean by that is there is some base, and the independent variable, the x, is actually the power. So if it's growing, it gets bigger. This is an example of a growth. A decay, you're going to see the same kind of shape of a graph, but it goes the total opposite way. So you should be able to recognize exponential functions just by looking at their graph. Then we should be able to recognize them by looking at their table of values. They should go exponentially big or exponentially small. So if we're looking at a table of values, now this one, this is the all-important y-intercept. When x equals 0, it goes through the power at 9, okay? Both of these do. So we know that the y-intercept, where it crosses the y-axis, is going to be at 9 on both of these graphs. You need to be able to identify if they're linear or nonlinear. When we're looking at the rate of change in these ones, we can see the difference in the y, or the rise, is going to be 3 every time you go up 1. So this should immediately remind you of y equals mx plus b. This is a line where the slope is 3 and the y-intercept is 9. This is a linear function, and I should be able to recognize that from the table of values. When I look at this, and there's a difference of 3, then a difference of 6, then it continues on, there's going to be a difference of 18. What you're doing is you are not just adding 3 every time like you did in a linear function. You're actually multiplying by 3. You're timesing by 3. For every x, when you go up 1, you have actually multiplied the y by 3. When you see this, this is going to be an exponential function when I see that in a table of values. So turn to your note to exponential growth, and you're going to see these table of values. There's that linear function we looked at, where y equals 3x plus 9. This is a line. This is the exponential function. Now let's look at a few parts of this exponential function. When x was 0, so think about 3 to the power of 0 is going to be 1, is equal to 1, y was actually equal to 9. So we found this numerical coefficient of 9 times 1. That is going to be in your exponential exponential function dA. Okay, that is going to be the y-intercept in an exponential function. Okay, the exponent, or the base that I'm multiplying by, because every time I've multiplied by 3, all right, that is going to be the base of this power that's raised to the exponent x. So when I plug in x equals 0 into this equation, I get y equals 9 times 3 to the power of 0, or 9 times 1 is going to be 9. That's how they got this. When I plug in the value of x equals 1, I'm going to get y equals 9 times 3 to the power of 1, which is 3, or 27. And then you can see when it's squared, this value is going to be 9 times 3 squared. 9 times 9 is 81. Okay, so this is going to grow exponential functions. Exponentially, these functions are non-linear. All right, so you should be able to write the rule for the function. X to the power of 0, that is going to give you your a. That meant you had whatever the base was to the power of 0, and you times it by your a. There is your a in your exponential function. So this equation is going to be y equals 8 times, you need to figure out the b. So what am I multiplying every time to get my new number? When you look at the pattern, you can see 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. This is the base. This is what you've multiplied your initial a by every time. So you have the equation is going to be 8 times 2 to the power of x. Okay, remember the idea that the exponent is only what is directly beside here. The base is going to be 2. Let's look at example 2. The 0, that tells you your a. When x equals 0, so a here is equal to 125. Now you have to figure out, what am I multiplying by every time? That is going to be your base. And probably just by looking at it, you can see every time I've multiplied that new number by 5, b is 5. So your exponential equation here is going to be y equals 125 times 5 to the power of x. Okay, we can graph these too. You always want to know what's happening around the origin when x equals 0. But you should pick a little bit to the left. We're going to pick -2, -1, 0, 1, and 2. We're going to plug those values into my equation and put them in my table of values. So I'm going to do a couple for you, because y equals 3 times 2 to the power of -2. Remember, when we have a negative exponent, that means I'm actually going 3 times 1 over 2 squared. Or this y is going to be at 3/4. When I have y equals 3 times 2 to the power of -1, this is actually 3 times 1 over 2, or 3/2. When x is 0, this goes to 0. You're going to get just the letter 3. That means it crosses the y-axis at 3. Okay? And then when x is 1, 3 times 2 to the power of 1 is going to be 6. 3 times 2 to the power of 2, or 3 times 4, your new answer is 12. So you can see it's increasing exponentially. When x is 1, you're all the way up to 6. When x is 2, I'm off the page. Okay, when x was 3, I was at 1.5. When x was 2, I was 3/4 of the way. This graph actually never crosses the y-axis. That's your exponential function. That's growth. I'm going to get you to do example 3 and 4 and 6 on your own, but I'm going to look at exponential decay. This is when it's getting smaller and smaller. The deal with exponential decay is that b is actually a fraction. All right, so you still have that initial at 0 when x is 0, where it crosses the y-axis, but this time you have an exponential function that is a fraction. So let's look what happens when I have solving for x equals -1. For times 1/2 to the power of negative 1. All right, you got to think about what we know about negative exponents. That's like negative 1 to the power of 1 and 2 to the power of negative 1. That means I would take the reciprocal of this, so it's actually going to be 2 to the positive 1 and 1 to the 1. Or 4 times 2 is 8. That's how they got y equals 8. And you can tell when y equals negative 2, it's still going to go way off this graph. There's your 0. And look what happens as it gets infinitely smaller and smaller on exponential decay. So the notes I want you to take is you still have this y equals a. A is where it crosses the y-axis times the b to the x. But if it is decay, then b is going to be bigger than 0 but less than 1. It's a fraction. All right? So let's look at example number 1. To find this rule, we have to look at what am I dividing by? I'm dividing by 3 every time. Okay, well remember what we know about fractions is dividing by 3 is the same as multiplying by 1/3. All right, there's our a. So y equals 3. My b is going to be 1/3 to the power of x. One more example. If you look, I'm dividing by 5 every time. That is the same as multiplying by 1/5. That's my b. So then I can write my new equation. Y equals 10, there's my a, right, times 1/5 to the power of x. Okay, let's look at graphing one of these functions. When you graph them, you should always pick around the origin. So I'm going to choose negative 1, 0, 1, 2, and 3. 3 times 1/3 to the power of negative 1. It is only the 1/3 that is to the base. That means I'm going to get 3 times 3 because the reciprocal will make this positive. This is not. When any 3 times 1/3 to the power of 0, anything to the power of 0 is 1. So when when x is equal to 0, y is 3. That's going through the y-axis. 3 times the power of 1/3 to the power of 1, well, that's going to be 3 times 1/3, or 1. So when x is equal to 1, y was 1. When it's 2, 3 times 1/3 squared, I'm squaring the top and the bottom, so I actually get 3/9, or 1/3. And this one's going to be 1/9. It's going to get closer and closer and closer to 0, actually never hitting 0. This is exponential decay. All right, try example 3, 4, and 6 at home on your own. So finish up those exponential growth and decay worksheets, and that's it for me. We'll see you Monday.